All right, let's put what we've learned here in this chapter on parallels and the previous chapter on congruence to work. And the way that I like to think of what we do in this class is we build machines, or we have tool sets, if you like. So we now have the tool set of congruence, which is side angle side and side 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 and angle side angle. We'll supplement that later in the chapter, together with results about parallels from here in chapter 5. So our parallel tests that allow us to know when lines are parallel, and also the consequences, that is, if we know that lines are parallel, conclusions that we may draw from that. So let me show you some of the kinds of problems that can be solved with those two tool sets. The first concerns transitivity. We, of course, have seen transitivity many times, and almost always up until this point in time when we have seen transitivity has been the transitivity of equality. And I've always asked you to give its full name, transitivity of equality, which means, of course, that in general, if A is equal to B and B is equal to C, then A is equal to C. Or as Euclid put it, if we have two quantities each equal to the same third quantity, that is A and C both equal to B, it follows that those two quantities are equal. Now, do note, and this is to reiterate, I've said this before, do note that this is a property in this case of the equality relation. The equality relation is transitive. And not all relations are transitive. Take, for instance, the motherhood relation. If A is the mother of B and B is the mother of C, it does not follow that A is the mother of C. As a matter of fact, it follows that A is not the mother of C. So some relations are transitive and some are not. And then here in mathematics, in our study of geometry, if we encounter a new relation, like the relation is parallel to, it is often a good question, is this relation transitive? So let us ask that question of the parallel relation. Is it transitive? And what that means precisely is this. If A is parallel to C and B is parallel to C, does it follow that A is parallel to B? That is, if we have two lines each parallel to the same third line, does it follow that those two lines are parallel? And no doubt you'll say yes. That seems quite obviously true. But as you know, it is not enough for us to simply declare that some statement seems true. We have to locate it within the geometrical system that we built. And the way that you do that is to identify it as a definition, a theorem, or a postulate. Okay? Now, it is not a definition. There's nothing in the definition of parallel or of line or of any term involved that would tell us whether this is true. And if I were to say that it is a postulate, you would no doubt accept that because it does seem quite obviously true. However, with the system that we have built so far, it is provable. And I think if a statement is provable, it should be proven. So let us talk about how it is that we will prove that if two lines are parallel to the same third line, that those two lines are parallel. I suggest that we do this indirectly. Okay, so what we'll do is this, is we'll assume that we have two lines, A and B, each parallel to C, but not parallel to one another. Okay. And that would give us something like what you see in the diagram. Okay, so what we're given is this, is that each of A and B is parallel to C, but we assume for sake of contradiction that A and B are not themselves parallel. Now the diagram, of course, looks very long, wrong, but we are long past the point where we allow a diagram, how a diagram looks, to substitute for the logic of a proof. So we've said that A and B are not parallel, follows from that they intersect. You see that in the diagram, they intersect at point P. And then ask yourself, how do we know? What in the system that we have built allows us to know that this is impossible? Well, here's a way to put it. We now have two lines, namely A and B, that both pass through point P, each of which is parallel to C. That clearly contradicts the Playfair postulate. Okay, so if we were to assume that A and B, each of which is parallel to C, are not parallel, we almost immediately contradict the Playfair postulate, which means that A and B must be parallel. So yes, absolutely, the parallel relation is transitive, and that is provable. Here's another nice little problem. Let's say that we have the setup that you see, two lines A and B with a transversal T and a pair of consecutive interior angles 1 and 2. And those angles are not supplementary. As a matter of fact, 1 plus 2 is less than 180 degrees. Okay, so I have two questions. First question, do lines A and B meet? The answer is clearly yes. Okay, if lines A and B were parallel, it would follow that angles 1 and 2 are supplementary. That's the consecutive interior angles consequence. But they're not supplementary, so A and B must meet. You might note that that's the contrapositive that I just took. Now, my second question is this, okay? Given that A and B meet, they meet, of course, either on the left side or on the right side of T. They cannot meet on both sides because lines cannot meet at 2 points. They meet at 1 point if they meet. So the question is it on the left or is it on the right? Well, let's say for a moment that it was on the left, okay? And I'm not going to attempt to draw this in. You can draw it in if you like. If 1 and 2 were to meet on the left, then of course on the left side of T, we would have ourselves a triangle. Okay? And I want to think about that triangle for just a moment. I want to think about one of the angles that would be in that triangle, the angle that I've just called 3. Okay, so again, we assume for sake of contradiction that A and B will meet on the left side of T, which means we'll have a triangle on the left side of T. And then 3 is going to be one of the interior angles of that triangle. Okay, so let's write down what we know. So here, first of all, is something we know. We know that angle 1 plus angle 2 is less than 180 degrees. That's simply the given. But we also know, of course, that angle 2 plus angle 3 is equal to 180 degrees. That's just simply the linear pairs theorem. And then we can draw a conclusion for this. And the conclusion that we can draw is this, just simple substitution, that angle 1 plus angle 2 is less than angle 2 plus angle 3. And now, just do a little subtraction. So subtract angle 2 from both sides. And think about what you get when you do that, and then simplify the result. You get that angle 1 is less than angle 3. And then to think about that. Okay, so again, if A and B were to meet on the left of T, we have a triangle on the left of T. 3 then is an interior angle of that triangle, and 1 is an exterior angle. Okay, and 3 is a remote for that exterior angle 1. And we know by the triangle exterior angle inequality that remote angles must be less than the exterior. They're exterior angles. So we have now contradicted the triangle exterior angle inequality. So it follows then that A and B cannot meet on the left of T, but we know that they meet, so they have to meet on the right of T. And that gets us our conclusion. Okay, so if we have a pair of consecutive interior angles that sum to less than 180 degrees, our two lines will meet on the side of the transversal where that sum is less than 180 degrees. All right, now let's talk about parallelograms a little bit. We now have the machinery in place, the machinery of congruence and parallels, to prove the core results about parallelograms. And first of all, let me define parallelogram. A parallelogram, as the name suggests, is a quadrilateral in which each pair of opposite sides are parallel. So I have a nice diagram for you. ABCD is a parallelogram with AB parallel to CD and BC parallel to AD. And the first results that I will have you prove are properties of parallelograms. So you'll be given that a quadrilateral is a parallelogram, and you'll prove certain properties of it. Here are the ones. You'll prove that opposite angles are equal. You'll prove that opposite sides are equal. And you'll also prove that diagonals intersect at their midpoints. That is, if you like, they cut each other precisely in half. And let's talk about one of these results, a really very easy one to prove. Let's talk about how it is that one would prove that opposite angles are equal. So how would one prove, for instance, that angle A is equal to angle C? Well, think about sides as potential transversals. Okay, so for instance, we could have the parallels BC and AD with transversal AB, in which case angles A and angles A and B are consecutive interior. Okay, but BC and AD are parallel, so it follows that angles A and B are supplementary. But then you can shift your point of view, and you can now take AB and CD as your parallels with BC as the transversal. Okay? And if we were to do that, then angles B and C would be consecutive interior, and our lines are parallel, so it follows that B and C are supplementary. So what that means is this, means that both angle A and angle C are supplementary. I'll try to indicate this in the diagram. Both angle A and angle C are supplementary to angle B. And then, of course, by the same supplements theorem, it follows that angles A and C are equal. And of course, we could prove that angles B and D are supplementary and equal in precisely the same way. Now, I'll also have you prove so-called parallelogram tests. These are ways to conclude that a given quadrilateral is a parallelogram. That is, if a quadrilateral have a certain property or properties, we'll be able to say that it's a parallelogram. And here are the ones. Okay, so we will know, or you'll prove, that if a quadrilateral has equal opposite sides, then it must be a parallelogram. That if it has equal opposite angles, it must be a parallelogram. That if its diagonals cut each other in half, that is, intersect at their midpoints, the quadrilateral must be a parallelogram. And you'll also prove that if you have one pair of opposite sides that are both equal and parallel, then you must have a parallelogram. So let's talk about just one of these. This will give you the flavor of how these are proven. And they're not particularly difficult to prove, but they are really nice examples of how the tool sets of the previous two chapters come together. And they're quite important results. They come up quite often. So let's say that we're given quadrilateral ABCD with opposite sides parallel. That is, AB is equal to CD and AD is equal to BC. And let us prove that it's a parallelogram. Before we launch into this, before I talk you through it, ask yourself initially, how could one conclude at the end of the proof that it is indeed a parallelogram? Well, at that point, you would have to just rely on the definition. That's really all that we've got. And the definition of parallelogram says a parallelogram is a quadrilateral with parallel opposite sides. So the goal would be to prove that opposite sides are parallel. And then, of course, make that final move where you declare that the quadrilateral is indeed a parallelogram. And then the question becomes, how would one prove that opposite sides are parallel? Well, of course, we would need to use the parallel tests. Okay, they will tell us the conditions under which a pair of lines have to be parallel. But recall how the parallel tests work. We need two lines and a transversal and then information about angle measures. Okay, so we're going to need to know something about angle measures. Well, how are we going to get information about angle measures? Okay, how will we be able to conclude that, say, a pair of angles are equal to one another? Well, this is where the tool set from chapter 4, from the congruence chapter, comes into play. That tool set will allow us to conclude in certain situations that angles are equal. In what situations? Well, when we have triangles and are able to prove them congruent. So it would seem then that we need to have triangles. And how would we do that? Well, presumably you would do something like this. You would construct a diagonal, AC. Okay, so that's like the crucial first step. Okay, construct AC. I'll write that and then I'll just talk through the rest of it. And then notice that we get angles. Okay, let's call them 1 and 2 and 3 and 4. And let's see if we can deduce that we have equal pairs of angles. Well, look at triangles ABC and, okay, so I called it ABC and CDA. Note the order of the letters, ABC and CDA. Okay, those are absolutely congruent. And how are they congruent? Well, of course, they share side AC in common. And then it follows that 3 sides of one are equal to 3 sides of the other. So those triangles are congruent by SSS congruence. And then it follows that angle 1 is equal to angle 4. So here's a conclusion that we'll be able to draw, that angle 1 is equal to angle 4. Those are angles that correspond to congruent triangles. We'll also be able to conclude that angle 2 is equal to angle 3. Once again, angles that correspond to congruent triangles. And now, you shift your point of view. Okay, so initially we looked at these as angles that correspond to congruent triangles. Now we look at them from the chapter 5 point of view. Okay, consider, for instance, sides BC and AD, top and bottom, with transversal AC. Okay, angles 2 and 3 are alternate interior. So we now know that for B and C, BC and AD, those two lines, with transversal AC, we have equal alternate interior angles. So it follows that BC is parallel to AD. And likewise, for lines AB and CD, left and right, with transversal AC, 1 and 4 are alternate interior, and they are equal, so it follows that AB is parallel to CD. And then, as I said a moment ago, once we know that opposite sides are parallel, we may, by the definition of parallelogram, declare that we have a parallelogram.